Hi class. Uh, Today we're going to start Unit 10. So I think Unit 10 is going to be the most useful one for many of your projects, and I think it's also probably the most useful thing we'll learn from statistics. I mean, I assume that many of you, like knowing how to compute a mean is obviously essential, but I think hypothesis tests are really the most advanced and useful thing that we'll be doing in this course for working with data. You can see the companion reading in the textbook. Um, I think this companion reading is really helpful for this particular setup. So let's get started. So hypothesis testing is, like what you imagine is where we form a hypothesis, and then we can assess if we think the hypothesis is correct or not. So here's an example we always like to think about. You might have a hypothesis that going to college increases your starting salary. So how would we prove that going to college increases your starting salary? So you can imagine we would get maybe, statistics on people who did and did not go to college, and then what their resulting starting salary is. Uh, and then you might maybe plot this. That's a good idea. You could compute correlation coefficient like we learned in maybe Unit 8, I think. Maybe it's Unit 7. Yeah, in Unit 7 we learned about correlation coefficient. You could even do the hist plots like we saw, where you have multiple, or we had the box and whisker plots, where you had the two plots, people who went to college, people who didn't go to college. But let's try to put an actual number to a hypothesis. The first thing we have to do is we have to learn how to actually prove hypotheses from a sort of logical point of view. So okay, let's start with this. So it's not really possible to prove this directly. I'll give a caveat there in a moment. But generally, the name of the game in engineering statistics is we want to disprove the null hypothesis. You go read any medical research, any psychology research, sociology, engineering. Whenever you see people working with statistics, they always set up a null hypothesis. Okay? And the null hypothesis is like the opposite of what you want to prove. Like if I wanted to prove going to college increases your salary, instead of proving that, I would disprove that not going to or that going to college has no effect on your salary. Okay? So the null hypothesis, the word null there, basically means there is no effect, no correlation, the most obvious thing is true. And instead of proving directly that going to college increases your salary, we're going to try to disprove that there is no relationship between the two. Now, there's this great branch of probability theory, pretty advanced branch of probability theory, advanced as in it requires some sophisticated math. Um, and it's about proving things directly, or basically causality. How do you prove things directly? It's kind of weird that it requires advanced math. It really, in some sense, doesn't, but it does because you need to eliminate a lot of odd effects. There's a great book, I should say, there's a controversial book that if you read will really enrich your understanding, and that's called the the Book of Why by Judea Pearl. He's a professor at UCLA. I think he's in mathematics. But it's a really interesting book about how to prove things directly, and it's sort of a different idea than null hypotheses. Anyway, I have high hopes for that field. I think that that's going to catch on, and a lot of it has to do with Bayesian inference. There's a strong relationship between them, although Judea Pearl takes a very different approach. I would say that it is an active area of research about how to prove things directly. And this may sound confusing to you because if you know from your history, like Aristotle and the Greek philosophers wanted to answer this question about how do you prove things directly. And surprisingly, it's an advanced topic in mathematics in 2020. But there you go, man. That's life. Okay, so, but for purposes of our class and what you will be doing in your engineering careers, we will almost always be disproving null hypotheses. And we're going to see why that is. There's a really simple, beautiful explanation of why it's a good idea to disprove null hypotheses. But let's work on what is a null hypothesis. So in this example, going to college has no effect on your salary. That's a very good null hypothesis. Um, you know, there's no need to, but I'll just mention that constructing a null hypothesis is not necessarily so simple. For example, someone could critique you and say, maybe we should only look at people who were accepted to a college but then didn't go to college and see what happened to their salary, and those who were accepted and did go to college and see what was the effect on their salary. So we'll sort of restrict the pool of people to those who were accepted to college. And we might even restrict it further because maybe some people who were accepted didn't go because they could not afford. So maybe we'll only consider people who could afford college, who got into college, and somehow we know they would have been motivated enough to complete college. Let's see if they have the same salary as those who did. So, like you could go on for a long period of time to try to construct the perfect null hypothesis. It's funny because you're going to try to build this null hypothesis and then shoot it down. So, because of that, if you construct a very strong null hypothesis, or not strong, if you can construct a very airtight null hypothesis, a null hypothesis that is really covers all your bases, like here, this last null hypothesis, then if you shoot that one down, that's strong evidence, right? You've removed the possibility that's just because people are richer who go to college. You've removed the possibility it's about motivation. You remove the possibility that it's about being intelligent, and you've really isolated only the effect of going to college. Okay. So I have a definition down here, and basically the idea is that the null hypothesis is the simplest possible explanation. So in our college example, the simplest explanation is there is no relationship between going to college and your starting salary. Another common null hypothesis is, let's say you have a drug and you're trying to see if it cures a disease. The null hypothesis would be the drug has no effect on the disease. So if you're trying to see if there's a relationship between, I don't know, what your grade is in 116 and how many hours you studied, the null hypothesis would be there's no relationship, there's no correlation. Okay. Now, one of the things about philosophy, this is very fundamental, there's no mathematical reason for this, the sort of a philosophy is that we should always by default believe the null hypothesis, right? We always should accept the simplest explanation. It's like Occam's razor or something, is that, the simplest explanation is always the best explanation. And I don't know if anyone's proven, mathematically or philosophically or whatever why that is. I think it's just usually an assumption that we want the simple explanation, or the simplest explanation that fits the data is the one we adopt. So that's why we always should have a null hypothesis in consideration. And then our goal will be to disprove it and reject the simple belief because perhaps, college does have an effect on salary. So the simplest explanation doesn't explain everything. So we want to look at rejecting the null hypothesis. Okay, so that's the name of the game. Okay, the name of the game for this lecture is we build a null hypothesis and then we disprove it, which lends evidence for our real hypothesis, right? Our real hypothesis that going to college has an effect on salary. Disproving the null hypothesis gives evidence for that hypothesis. Or we fail to disprove the null hypothesis. So there's a lot of negatives going on here, right? So we're not actually failing to prove our hypothesis. We might fail to disprove the null hypothesis, right? It's like maybe that's a triple negative. I don't know. It's confusing to me. But basically, sometimes our evidence is not strong enough to reject the null hypothesis. And that means that either A, we need more data, or B, maybe our hypothesis is wrong and the null hypothesis is correct. Okay. So one of the beautiful things about hypothesis testing, the reason that it's so compelling, is that by assuming the null hypothesis is correct, it makes all of the math super simple. By assuming, so our goal is to basically assume the null hypothesis and then find out and then reject it. So that means our assumption is the null hypothesis. So, right, if we're looking at two pieces of data, by assuming the null hypothesis, we assume they're not correlated. Then we are going to see, does that hold up? So one of the cool things about the adopting the null hypothesis is that the math is much simpler. And that's why some of these other approaches, like I mentioned about causality or evidence for a hypothesis, they're more complicated because you have to sort of construct your hypothesis mathematically. But if you assume the null hypothesis, the math is very straightforward. Yeah, this is all abstract. If that didn't make sense to you, I would recommend you just think about it a little bit, and then once we've seen a couple examples, go back and think about it again, and it should clear it all up. Okay, so here's our simple example. Say I open up a cash for gold store. Okay, maybe maybe someday malls will reopen, and then I open up a cash for gold store, and people bring me their jewelry. Now let's say I know that if I just, if I get some random jewelry, and if that jewelry is made of gold, its melting point is a normal distribution with a mean of 1060 degrees. Okay, so I have, this is how I check. I have some instrument, and I melt the gold. I check the temperature at which the metal starts to melt, and that tells me A, if it's gold, and B, you got to melt your gold to turn it into money. So, cash for gold. And let's say that I've done this for a long time, and I know that if whenever I go and get some real gold, typically the actual melting temperature is normally distributed with a standard deviation of 3 degrees Celsius. How do we know it's normal? Well, that's the central limit theorem, is that probably there's many things that go into it, like lots of different impurities. My instrument could be wrong. I could have mistakes, like I didn't look at the instrument quick enough. Lots of reasons why it's, there's normal distribution, because many sources of error add together to give me normal distribution. So that's the setup. I know that gold is normally distributed with a mean of 1060 and has a standard deviation of 3. I melt a sample. So someone gives me, like this is my grandma's necklace, and I want to turn it into cash. So they give me grandma's necklace, and I melt it, and it melts at a temperature of 1045 degrees C. Is that suspicious? Okay, or is that gold? Is this example of jewelry coming from gold? All right. So let's set it up. So the simplest explanation is that the sample is gold, right? Why is that the simplest explanation? Because any other explanation I could have, like the sample is palladium, the sample is gold cut with, I don't know, copper, any other explanation is going to be more complicated and require more parameters. But if I assume it's gold, then I know the distribution of gold, I know the parameters for the probability, so it's the simplest explanation. So my null hypothesis is that it's gold. So let's see if we fail to disprove the null hypothesis, or let's see if we disprove the null hypothesis. Okay. So what I might want to do is I want to say, what is the probability that a sample of gold had a melting point of 1045 degrees, right? Well, that would give me evidence for my null hypothesis. Is that maybe the probability of a given sample being 1045 degrees, if that probability is high, right? If it's highly likely that gold will melt at 1045 degrees Celsius, then that's strong evidence for my null hypothesis. If instead 1045 degrees is a very unlikely melting point, then it's not likely that it's gold. But we have a problem here, is that my probability distribution for gold is continuous, so I can't actually query about a single point. I can't actually compute the probability of exactly 1045. So I'm going to do kind of a trick. Okay, I'll show you guys the picture. It'll make a lot more sense, and we'll go back and look at the math. I'm going to say that I want to construct an interval that includes that 1045 degree value. So here is my probability distribution for gold. Okay, it's centered at 1060. And I want to say, what is an interval width that would just be big enough to catch my sample? Right, so I can't compute the probability of this sample. I can't compute it directly, right? Because we can't get probabilities of single numbers for continuous values. So instead, I'm going to construct an interval, because we can compute probabilities of intervals. So I'm going to construct an interval just big enough to catch this value. Now you might be thinking, why is the interval centered here? Why isn't it, over here or over here? Well, I'm going to make it centered at the mean, because basically I would expect that if it's close to the mean for my distribution, that I should have a small interval, because it's a very, unlikely that it would fall outside of the interval. Okay, so let me say that another way, is that I want to relate the area of this interval to how likely the null hypothesis is. Okay. So if I had a number that's like 0, right? Like someone says this is gold, they hand it to me, and I go check the melting point and it's 0, right? And it's ice, it's water actually. I should how big this interval should be how unlikely the null hypothesis is, right? So like if this area is huge, right? So I'm actually thinking about falling outside of this area, so maybe 1 minus this area. Okay, so this is a long way of saying that how likely I believe the null hypothesis is related to what this area is. If things are farther away from the mean, the interval gets bigger and the area gets bigger. If things are close to the mean, the area gets smaller. and my evidence for the null hypothesis changes. So let's now look at the math here. So what this means is that I construct an interval, and that interval is related about how far away from the center of the distribution it is. So my distribution is centered at 1060 degrees Celsius. I look at what is my single point, 1045, how far away is it from that center? Then I compute the probability of that interval. So I just go to a standard normal using a z-score. I construct the interval and get the probability, and it turns out that interval area is 0.9999999. So what does that mean for the null hypothesis? So we have to do a little bit of logical thinking. So I'm telling you that the area of the interval is related to how likely the null hypothesis is. But we need to figure out if if more area means more evidence or more area means less evidence. So if we had a sample that melted right at the mean, so the mean for gold is 1060, and let's say that my sample melted right at 1060, then we should believe the null hypothesis, right? We should believe the null hypothesis. Well, that interval would have an area of 0. So if the area is 0, that means it should be strong evidence for the null hypothesis. If we had something very far away, the area would be big because the interval would be big. So then what we will say, and this is true, is that the p-value, the probability, I don't want to say probability of the null hypothesis, but I'll say that for now. So the probability of the null hypothesis is 1 minus the area. Okay. Now it's not actually a probability for the null hypothesis, and the reason why is that there's no well-defined sample space and no well-defined normalization. So I'm not going to call it a probability. I'm going to call it a p-value. Okay. Now it is kind of a probability because like this interval is a valid probability, and I'm taking 1 minus the interval, but we're just going to call it a p-value. So what I'm saying is that I'm going to say how likely the null hypothesis is by taking 1 minus this area. So a high p-value or a low area means that my null hypothesis is likely correct. A low p-value or a high area means my null hypothesis is unlikely. Now, what does the word likely mean here? Likely is when you have a probability that's not normalized. Okay, so people will say things like likelihood or something is likely or the likelihood of this. That just means that I have a number for it, like I can give a number like 0.999, but it's not well normalized or it can't be normalized. So that's what happens when we say the word likely. So that's how likely null hypothesis is. Okay. So this is a lot of talking, and I want you guys to get the conceptual understanding of it, but it's mechanically very simple. It's mechanically very simple, okay? So here's what happens is that we computed the p-value, and we computed it to be 0.0000001. And that says that the probability of seeing a value outside of this interval is 0.000000001. Means it's highly unlikely that the sample is gold. It's highly unlikely the sample is gold because we would expect to see a value in the interval, outside of the interval, this often. Okay, so then my p-value is 0.0000001. So then the question is, what does this have to do with the hypothesis, right? Did we disprove or did we prove the null hypothesis? What we do is we just, by convention, we say that if the p-value is less than 0.05, we reject the null hypothesis. That is p-value representing the likelihood of our, I don't know, I can say probability, but it's not really probability. If the p-value is 0.05 or below, that means we can reject the null hypothesis. And we call that our significance level. Okay, so that means that we have observed something significant, or it is significant when we have a p-value of less than 0.05. That means that the null hypothesis is unlikely. It is unlikely true. The null hypothesis is unlikely to have occurred. So what does that mean? Why p-value of 5%? Why that? Why is it that? We're saying that the interval in which our sample occurred is where a sample would occur randomly 5% of the time if the null hypothesis were true. So think about the interval we set up. We're saying that if we were going to go test, so let's take the p-value we actually had. The p-value was like 1 times 10 to the 8. If we have 1 times 10 to the, 1 times 10 to the minus 8, right? That means that we would expect samples to fall in that interval where that weird sample is 1 times 10 to the minus 8 times of the time. So very low probability of being in that area. Okay. So basically, we assume the null hypothesis, we compute the p-value, which is the probability of the interval of where our sample was, and then if that p-value is less than 0.05, we say we reject the null hypothesis. If that p-value is greater than 0.05, we say the null hypothesis is still possible, it's likely. And then at the end of the day, we say, okay, we have evidence that our hypothesis, that it's not gold, we have evidence for it, and that evidence is that we rejected the null hypothesis, and that it's significant that it's not gold, or it's significantly likely it's not gold. Whew, okay. A lot of kind of weird mental gymnastics for this because we are not proving things directly. We're working with a null hypothesis. And then there's other mental gymnastics as well because we're not talking about the probability of the sample. We have to do probabilities of intervals because we can't calculate probabilities of samples. So we have to look at things like intervals. Okay. So that's kind of it. We're going to see a couple more examples. But that's kind of the name of the game, is basically you take the null hypothesis, compute the probability of an interval, which just includes or just does not include basically an interval where the boundary of the interval is on your sample. Then you turn that interval into a probability by calculating the probability of the interval under the null hypothesis, and then that's your p-value. Then you check your p-value against your alpha value, which is always 0.05 for purposes of this class and life, And then if that p-value is less than 0.05, you say, we reject the null hypothesis, something significant is happening, this is interesting, this is exciting. If it's greater than 0.05, you say, uh-oh, the null hypothesis could be true, we don't have enough insight, we don't know anything, we need more data, or, this is a boring problem. Insignificant result. Okay. So let's do another example. Okay. This is a more complicated example. Now I have multiple pieces of jewelry coming in, and I do not know the standard deviation. Okay, so again, we have jewelry coming in. We don't know the standard deviation. All I know is that, maybe this is my first day at Cash for Gold. Okay, it's my first day. And I look up on the internet what the melting point of gold is. And then I get my first, I get 5 pieces of jewelry from someone. And I want to know, is it reasonable that the sample's melted at 1045 Celsius? Okay. So in this case, I'll have 3 samples, okay? So I have a couple samples. So I'm going to use my samples to estimate the standard deviation, and then I'm going to see if it's likely to have come from the same distribution as the gold distribution. And remember, you might look at this and say, hey, Professor White, my samples might not be gold, so how can I estimate the population standard deviation of gold using my samples? Well, remember, I'm assuming the null hypothesis. So I'm assuming that these are gold, so I can then estimate the population standard deviation of gold using these samples. So it's kind of a cool thing about the null hypothesis. By accepting the null hypothesis, I can use my samples as ways to estimate the parameters for my population distribution. Okay. So the way we're going to approach this is like we did in the first one. We start by constructing a null hypothesis that corresponds to a probability distribution, or probability mass function, probability distribution function. So it could be continuous or discrete. Then we compute an interval which includes values that's extreme as your sample data. That's a fancy way of saying we're going to build this interval that just barely doesn't catch that sample, and then we're going to look at the complement of it. So remember in our Cash for Gold example, we built that interval that just does not include the sample, and then we looked at 1 minus that. So we're looking at the complement of that interval. Now this can be like we did for confidence intervals. It can be single or double-sided. And this kind of depends on what is your idea of extreme. So for melting metals, right, you could have metals that melt higher than gold or less than gold. But if you're looking at maybe, you want to know if someone's cheating you on the gold, maybe you only care about if it's the melting point is lower, because whenever there's impurities in gold, it makes the melting point lower. So maybe you only care about lower things. Okay. So once you've assumed the null hypothesis, you've constructed your interval, then you just compute the probability of the interval, and that's your p-value, and then you check it against 0.05. So let's go back to the example where we have multiple samples. Okay, here's some samples, and we're going to use the t-distribution, and this hypothesis test is called the student's t-test. By the way, this is where the student t-distribution comes from, is from this hypothesis test. Okay, and more fun information. The name student, right? It's a weird name. It's because there was this scientist, I don't want to say scientist. There was this engineer who worked at a brewery, and I want to say it was the Guinness Brewery. We're going to go with Guinness. He worked at the Guinness Brewery, and he was trying to compute some statistics of brewing beer. And he had discovered this distribution, this t distribution, and he wanted to publish it in a statistics journal. So he asked his employer if he could publish it under his name. Well, the employer didn't want his name. I don't know why, So he decided to publish it under the name student because he, was a student of statistics. So it's called the student t distribution. And every element of that story is probably wrong, but there you go. I think it's a fun story about where the name student comes from. So it wasn't somebody named Mr. Student. Okay. So here's how we approach this. We assume the null hypothesis, then we compute uncertainty and the true mean or the population mean using a confidence interval. Then that is our probability distribution. Then we compute the interval, then we compute the p-value. Okay. So like the steps we had before, we compute a probability distribution. In this case, we will use that population mean uncertainty thing we learned in Unit 8. And then we will compute an interval on it, then compute a p-value. Okay. And I think this whole lecture, I feel like you should rewatch this once you've done a few problems, and it'll make a lot more sense. Okay, so here's the setup. We first of all need to get this distribution. Okay, this distribution, and that's going to be the probability of the sample mean. Okay, you can also view it as the probability of the population mean, but basically, just like when we did confidence intervals, we're going to build up a probability distribution describing how far away the sample mean is from the population mean. So recall that that is a t distribution who is centered at the sample mean, right? Or centered at the population mean. You can do it either way, but let's say it's centered at the sample mean. And then the standard, or the second parameter, the variance of this distribution, it's the standard error. And then because it's a t distribution, we have to put in the degrees of freedom. In this case, we had 6 samples, so that's 5 degrees of freedom. And that gives us a probability distribution. So let's see what that looks like mathematically. Here are our samples. We compute the sample standard deviation, compute the sample mean. We know the population mean should be 1060. So now we're looking at the distance between the population mean and the sample mean, okay? Then I'm plotting the t distribution. So the t distribution here is going to be centered at the population mean, or it could be at, the sample mean minus population mean. And this is just setting up that distribution. I'm not going to go into the rest of it, but just, we'll see how to solve the problem in just a second here. Okay, so here we go. Here's how we solve the problem. Again, get the samples, standard deviation, sample mean, the true mean, and the population mean is here. Then what we do is we want to get an interval, right? We want the probability of an interval. Okay. The interval is going to be the extreme values. So it's going to be not the centered one, right? It's going to be 1 minus that, just like last time. So what we need to do is get the t value. Okay, we're going to get the ends of the interval. So you could either set up in Skippy stats, you could set up the t distribution with the parameters here, or you could compute the t value for the standard t distribution. That's what I'm going to do here. I'm going to find the t for the standard t distribution. So we take the distance from the population mean. So we take the sample mean, distance from the population mean. Then we divide it by the standard error, which is the sample standard deviation divided by the square root of the length, or the number of samples. Then, which interval do we want? Again, we want the extreme interval, so outside of the center. So why does it say integral from minus t to t? Just a moment here. Oh, yeah. Okay, this statement here specifically want to find the integral from minus t to t. That's saying we want to build this interval, but then we're going to take 1 minus it. I should just put 1 minus in there. Anyway, so we want the extreme interval, not the inner interval, we want the outer interval. In this here, what I'm showing is that if you compute the inner interval probability, then you can take 1 minus that. That's all I'm getting at there. Okay. So then I compute the probability of the interval. In this example, I did it for both single and double-sided. It's maybe a little bit complicated of an example, but if I look at the outside interval, it's 0.039. Okay, so sorry, if I look at the double-sided interval, it's 0.039. If I look at the single-sided one, it's 0.019. And so one thing about single and double-sided is you can always compute everything as a double-sided, and then if a question asks you for the single-sided one, you could just divide the double-sided by 2. Okay, so that's how you get it. That only works for symmetric distributions. That works for like the normal, the binomial, exponential. No, not exponential. Normal, binomial. Then for the geometric and the Poisson, this doesn't hold true because they're not symmetric. But for the normal, which is what we deal with almost every time, and the t distribution, these are symmetric. So if you have a double-sided and you want to go to a single-sided, just divide your p-value by 2. Okay. So this is just a little bit of discussion if you accidentally reverse your area. It's okay. Like, we computed this probability of the interval, and then we compute this p-value. If you accidentally switch the area around, that's okay. You'll be able to figure it out because you just need to remember that you want your p-value to be very small when you're far away from the center of your distribution. Or to put it another way, if you're in a situation where it's highly unlikely the null hypothesis is true, you should have a low p-value. So if you're looking at like your population mean is here and your sample mean is really far away, then you should expect to have a low p-value. So you can always double check that. And another thing that happens a lot of times, your area will come out to be negative if you swap your t values. Then you just know, okay, it accidentally got negative ones. All right. So there's a lot, like I'm teaching here and discussing it, so I would just want to show this example one more time and just show you guys how quick it really is with all of this work. Okay, so open up a little Scratch notebook here. I think this is a different. Ignore that. Okay. Okay. I just want to show you guys how simple this really is. Okay. So here I am, right? My samples. I have my population mean, and all I would need to do is construct an interval. And let's just look at that, right? So let's just look at that. All I need to do is construct my interval. So I will take my true mean minus my sample mean. Okay, and I need the standard error. And remember, the standard error is just sigma over the square root of the number of samples. I don't even need to compute the t. Let's just use the distribution directly. We know from our homework that I want to compute the probability of an interval. Okay, so I'm going to use CDF, right? I want to compute the probability of an interval. So I want it to go from one value, want interval that is symmetric. Okay, so remember CDF goes from minus infinity to my value. So I want an interval around true mean, population mean. Okay, so I want an interval around that. Okay, so let's go from the true mean up to how far away the sample mean is. So let's figure that out. So let's just, let's figure that out here. So my sample mean is here. Okay, so let's say the distance is going to be the distance between the true mean and the sample mean is this. So basically, my sample mean was 18.8 degrees away from the true mean. So I want to make an interval that's minus 18 plus 18 from the true mean. So I'm going to get plus the distance. And what is the distribution parameters? Well, it's a t-distribution. And we know that the t-distribution is going to be centered at the population mean. Oops, the true mean. And it's going to have a standard deviation, which is called scale, of the standard error. Then we have the degrees of freedom, which is the number of samples minus 1. Okay. So that gives me from minus infinity to above the true distribution. So we have to subtract minus this to below. All right. So p-value is 0.96. I switched it, right? Remember what I think I said this. So we want, this is the inner interval, right? So this is the inner interval. We want 1 minus that. So 1 minus this. Okay. So there's our p-value, 0.039. Okay. So where do these numbers come from? This is it's a t-distribution with centered at pop mean. Scale is standard error. Degrees of freedom is n minus 1. We remembered that the probability of a sample mean is following that. Okay. All right, so let's talk a little bit about that 1 minus part, right? So just remember, we want extreme area. We want the interval area away from boring slash center slash null values. Okay, so we want the extreme values. So by doing this first calculation I did here, this first calculation, so this is currently from just below pop mean to just above pop mean. So we're saying that I'm calculating the interval for where sample mean lies, and I'm saying that it's just right by the population mean. So that's why this first area I came out is not for extreme values, okay? But if I do 1 minus this, okay, now it's the interval that's interval away from pop mean, right? This is the interval away. So like if I'm viewing my interval like this, I have extreme, 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 extreme. Then I have, I'll just say near population mean, and then we have the extreme, 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 extreme. So this is my first calculation I did here. These are values near the population mean. Then if I do 1 minus, I get the complement, so I get, these other extreme values, okay? And that's the p-value, all right? Then we just compare that against alpha. So if I put all of this together, this is the calculation, okay? And then I might also do, is this less than 0.05? So true. So we reject the null hypothesis. Now, if I want to go even simpler, I can use t-values, and I can just say this. I can just say t equals pop true mean minus sample mean divided by sigma divided by impedance square root, like samples. Okay, and then I would just do p equals 1 minus, hold on. All right, so I left off um, showing you how to compute it just using a t-value. So there we just do minus t, but we must put in the degrees of freedom. And then again, the 1 minus. All right, what did I do? Oh, this is already negative. Excuse me, the true mean. I think this is already negative, is that right? The other one was negative. You know, this is why I wrote that section in the lecture on what happens if you switch your t-values. Oh, no, right. If it is positive, then the integral to go from minus t to t would be this. Yes, and there we go. Okay, so there you go. And you notice, actually, I did have my t's switched. And you notice the value was like 2, right? And you should recognize that that's not a valid probability. So I think, you know, the most dangerous thing is if you get something like this, you forget that 1 minus, but you have your t's the right way around, and you get this like very high p-value. You should always be a little bit suspicious of high p-values, you know, and make sure your math isn't incorrect. Okay, so I think that's all I want to cover for the student t-distribution. You know, it's not too hard. Um, and we'll see. I think once you do a couple examples, you see it's not too hard. I think the most common mistake for people working on that is that where did I put that? Is that we're computing probabilities of intervals, so we use CDF. We're using the cumulative distribution function. And then don't get that confused within Unit 8 when we were computing confidence intervals. We were finding intervals, right? We're computing confidence intervals. We're finding the intervals. So there we were using PPF. It's a small difference, but when we were doing t-distributions last time, we were using PPF. Here we're using CDF. Okay, so basically to summarize, we saw 2 hypothesis tests. The first is called the ZM test, and that was the one where we had a single sample, but we knew the population standard deviation. In that first example where I said I know the population standard deviation for gold is 3 degrees Celsius. So the ZM test allows you to compare measurements and ranks. So basically, you could have measurements like the melting point of gold or something like that, or you could have ranks like this is the hottest sample, this is the second hottest sample, this is the third hottest sample, something like that. It allows you to compare a single sample, like one sample of gold, versus a normally distributed population. And this normally distributed population could be from central limit theorem, or it could just be, a normal distribution, right? So here we had gold with a known population standard deviation and a known population expected value or known population mean. Our null hypothesis is always that that one sample we saw came from the same population as the normally distributed population. Conditions, we need to know the population standard deviation. So that's kind of a hard condition, but sometimes it can be helpful. And then obviously, if we don't know the standard deviation of the population, we can use the second test we saw, the student t-test. So the way we use it in Python is you could integrate using IRF, but we almost never use that in this class. So you can use the Skippy stats normal. Should be SciPy, not skipped. Okay. Then the student t-test is the same, except for we don't know the population standard deviation, and therefore we estimate it with samples. So the student t-test, we need to have multiple samples. Now, what if you had samples, but you knew the population standard deviation? Then you could still use the ZM test, but you would take the sample mean here instead of, just using the single value. Okay, so that's all I want to cover for this lecture. A lot of conceptual stuff. In the second lecture on hypothesis tests, we'll see a bunch more examples of how to do them with just different distributions. But the main thing, the main takeaway, and I'll put it up here again, is basically we start with a null hypothesis that gives us a probability distribution function. And then what we do is we compute, then we find an interval, then we compute the CDF of that interval. And our intervals are always the extremes. We always want extreme intervals. So always stuff outside of like normal, right? That's what we want to do. So like before we saw we have that interval in the middle, and that gets bigger as we have more unlikely values, but we want the opposite. We want the p-value. We want to get low p-values, so extreme values. So we compute the probability of the extreme interval, and then if that probability of that interval is less than 0.05, then we say the result is significant, otherwise not. Okay, so that's it for hypothesis tests. We'll see a few more hypothesis tests later. And like I said, I think you guys will find hypothesis tests are really useful for assessing significance of data and being confident in conclusions like I think there is a correlation or there is no correlation, or I think this has an effect or this does not have an effect.